Okay, so today we are talking about net ionic equations. I've given you a note-taking guide to assist with this. So net ionic equations represent the chemistry of what actually happens when I take two solutions and I mix them together. All right, so for instance, if I've got a solution made from dissolving sodium bromide in one solution and I've got another solution made from dissolving chromium 3 acetate in it, when I combine those, what's going to happen? Okay, that's what we talk about when we write net ionic equations. So that represents the chemistry of what happens when two solutions are combined. And you've done this in lab. A lot of the labs you've done have been solutions that you mix together and you form some sort of precipitate. So the lab that you turned in on limiting reagent, remember you made two solutions, you mixed them, you formed a precipitate, you filtered it, you dried it, you weighed it, right? That was all based on net ionic equations, and you could actually write a net ionic equation for the lab you just turned in. So these are the steps that you go through to write a net ionic equation. The first thing you do is you write a molecular equation. You write a molecular equation. A molecular equation is the same thing as a double displacement reaction. All right, it's the same thing as a double displacement reaction because all of the ones you're going to be dealing with in intro chem are going to be double displacement reactions. So let's just refresh our memory on what that means. A, B combined with C and D. Now remember, the cation of the first salt gets together with what? The anion or the cation? The cation gets together with the anion, right? So you get AD, and then the anion gets together with the cation, right? Because you have to have a cation and an anion. You have to have a cation and an anion, right? And then when you write these formulas here, make sure you crisscross your charges, yes? Because you can't just say, oh, there's a subscript 2 here, so I'm going to necessarily need a subscript 2 here, right? These subscripts come from crisscrossing, so always make sure you re-crisscross those. Okay, so this is the same thing as a double displacement reaction. That's nothing new there. And now what you're going to do is you're going to look up the solubility of the products. Solubility. Solubilities, I should say, of the products. And this is going to be in your solubility rules, which I have put on your handout. And then let's fill in this part and then we'll talk about the solubility rules. Write something that is soluble as AQ subscript and write something that is insoluble as S subscript. You wouldn't believe the number of people who will say, oh, S stands for soluble. That's not true. Please don't think that. Okay, what does that S stand for? This is the state of matter. Solid, right? This S stands for solid. So something that is insoluble is a solid. Okay, that's why it's S. Something that is soluble means dissolved, and this is being dissolved in water, right? And something that is dissolved in water, we say, is an aqueous solution. That's why it's AQ. Okay? So please don't think S stands for soluble. Please, it doesn't stand for that. S stands for solid. Okay? And remember, the something that is insoluble, that's also known as the precipitate, right? If I said, what's the precipitate? You would say, whatever you put the S next to, that's the precipitate. And you don't always have a precipitate. We'll go through some examples where you don't. But let's first revisit those good old solubility rules and make sure we understand how to read them. I can't remember if the one on this handout is the same one that's in the current edition of your textbook, but it's very similar if it's not the exact same one. So here's your solubility rules. This might not even be the same one that I gave you last time. I can't remember. Solubility rules all work pretty much the same way. Right? Oxides and hydroxides are insoluble except NaOH, KOH, BaOH2. Cross this one out. Okay, CaOH2 is insoluble. It's a precipitate. You're going to get a precipitate in this class every single time, right? We talked about this last time, I remember, because I said, you know, when you dissolve a salt in water, all of them dissolve, just not all of them dissolve very well. Do you remember talking about that? And I said, well, when you get to Chem 2, you'll learn about why some dissolve well and some dissolve very poorly. But calcium hydroxide, in this class, you're always going to see as a precipitate. You're never going to see that as soluble. So just cross that out. I think this is pretty similar to the one that I gave you last week, but they all work the same way. Okay, so these are your ions. This is the rule, and then if there are any exceptions, they'd be after. So like, for instance, with nitrate, there are no exceptions. So all nitrates are soluble, no exceptions. Most of these sulfates are soluble except, most of these are soluble except, these are all insoluble 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 except. Do we understand how to use this one, the solubility chart? So again, if I gave you one that's slightly different from this last time, I can't remember what the exact one looked like. They all work pretty much the same. Does it make sense how to read this chart versus the previous one? Okay, so that's step one. You write your molecular equation, and I forgot to put this in the rules too. Make sure it is, write a, add this word, balanced molecular equation. Okay, it's got to be balanced, because if it's not balanced in step one, step two comes from step one. So if you get it wrong in step one, this is one of those domino effects. It's going to be wrong in step two, it's going to be wrong in step three. Okay, so make sure you have a balanced molecular equation. Don't leave it unbalanced. It needs to stay balanced, because you're going to carry step one down into step two. Okay, now let's go to step two. So you're going to take your answer from step one, and you're going to turn your molecular equation into a complete ionic equation. So this is a little bit of writing. I'm going to warn you. It does involve a little bit of writing, but it's not hard. There's no math. Okay, that's the nice part. There's no stoichiometry to worry about. This is just a whole lot of writing. So you're going to take your molecular equation and you're going to turn it into a complete ionic equation. So that means that everything that has the subscript AQ, you're going to write it as its ions. So for example, if you have KBr AQ in the molecular equation, that becomes K plus AQ plus Br minus AQ. You're breaking it back up into its ions, is what you're doing. So that means you need charges, okay? You must have charges. You will lose points if you don't put those charges, okay? Because K, sodium metal, when you add that to water, you get explosion, big mess. Sodium ion in water, I'm sorry, potassium ion. Potassium ion in water, no big deal. Same thing. Potassium metal in water, potassium ion in water, don't drink it, okay? Do we see the difference? You need that charge. Okay, because losing that electron makes a big difference. Sodium metal plus water, bad idea. Sodium ion plus water. Okay, same thing here. Bromide versus bromine. Bromine in its elemental form is a brown gas. It's Br2. Bromide, the ion, very different. Okay, so make sure when you dissociate this in step two, if it's got the AQ subscript, you got to split it back up. You got to uncrisscross those charges. So also be careful of this. if you have, say, CaCl2aq, and you're trying to dissociate that, how does that dissociate? That becomes Ca2 plus Aq plus what? There's a subscript of 2 here. I'll give you the 2 choices. You pick the correct one. Cl2 minus or this. Which one is it? It's the bottom one. Why is it not the top one? Just ask yourself, what is this compound made out of? Is it made out of calcium and this, which by the way doesn't exist? That's non-existent. Or is it made out of calcium and 2 chlorides? It's made out of calcium and 2 chlorides. Okay. There's Cl2, the green toxic gas. You want to avoid that, right? Or there's chloride ion, no big deal, right? As long as you don't ingest tons of it, you'll be fine. Do you understand why it becomes this and not this? That makes sense, okay? I see this all the time and I want to scream because it doesn't exist. There's no such thing. Yes, exists? No, doesn't exist. So uncrisscross, and then if it's a subscript, it needs to come out as a coefficient, okay? So that's where most mistakes get made, is in this part right here. Now, if you have something that is solid, or if for some reason you produce the gas, you just leave it alone. Don't touch. Do not touch it. Just leave it alone. Because if it's a solid, that means it's sitting there at the bottom of your beaker. It's not dissociated. It's just sitting there, right? That means it's a precipitate. It's sitting at the bottom of your beaker as a chunk. Or if it's a gas, it bubbled out. Right? Now you're going to take your answer here, and you're going to turn your complete ionic equation into a net ionic equation. All right, so what does that mean? Well, when you write the complete ionic equation, you will find yourself writing the same thing multiple times. You're going to feel redundant. What you want to do is you want to cross out the spectator ions. And so these are the things that appear on both sides. And they must appear exactly. So for instance, if on one side you've got Cl minus Aq, and then on the other side you've got 2Cl minus Aq, something's wrong. You need to go back and double check your complete ionic equation because the coefficients should match exactly. And if they don't match exactly, you need to go back and double check up here because they should match exactly. Coefficient and charge and everything. So you just cross those out. And what you're left with is the net ionic equation. Okay, I know this sounds kind of like a bunch of goobly-goop right now, but when we go through examples, I think you'll see it's not really that bad. So the last thing we need to do before we get into some examples is the scenario called no apparent reaction, NAR for short. This occurs when both products are soluble. What's that sound? Sounds like some sort of alarm. Both products are soluble. All right, so what happens here is, well, I'll show you some examples of NAR. I'm not going to make one up on the spot. We'll just do some examples. And so if this occurs, I'll show you what to do. But in other words, everything's going to be a spectator. So there's no actual chemistry happening. You're just making a solution. So let's do some examples. I printed your page so that you've got basically a blank page. Right, because here, this is practice that you'll be doing in a minute, so just disregard that. The second page I left blank on purpose so that you could have a place to write the examples that we're going to do in class. Turn that So let's do some examples before I give you time to practice those ones that we talked about. Okay. Right, balanced, molecular, complete ionic, and net ionic equations for the processes that occur in solutions of sodium, I don't know if iodide's on there, bromide, and copper 2. Solutions of sodium bromide and copper 2 nitrate are mixed. So here's an example. All right. My cursor's flashing in my face. So first thing we need to do is we need to write a molecular equation. So we write our reactants. Sodium bromide. Sodium ion has what charge? Bromide ion has what charge? So when we crisscross those, that just becomes NaBr. Okay, and that's got AQ because it's a solution. Now let's write our other reactant. Copper 2, what's that? Cu with what charge? 2 plus. And nitrate, what's that? NO3 minus 1, right? So we crisscross those, we get Cu NO3 2 AQ, right? Because this comes out here, put parentheses around it, this comes down here. Okay, so this is a double displacement reaction, right? So that means that sodium ion is going to get together with nitrate ion, right? So Na plus and NO3 minus. When I crisscross those, what's the ratio? It's just NaNO3, right? Now leave yourself a blank so we can go look up its solubility. And now let's combine these two together. Copper 2, so Cu2 plus, right, because it's copper 2. And bromide, Br minus. We crisscross those, what are we going to get? CuBr2, right? And again, save yourself space, because we'll go look up their solubility. Now we just need to balance this. Clean up my mess here. That big space. NaNO3 is going to need a coefficient of what? 2. Right? Is there going to need to be a coefficient anywhere else? 2 in front of NaBr. 2 in front of NaBr. Right? Got to be balanced. But now let's look at our solubility rules and figure out what's the state of matter for our products. So flip back over to your solubility rules. Let's see, for nitrate, all nitrates are soluble, so this is just AQ. And bromides, most chlorides, bromides, and iodides are soluble except Ag, Hg2, Pb, and Hg. So this one's aqueous as well. Now here's how I'm going to demonstrate no apparent reaction, because it just makes the most sense when you see it. If we go to step 2, convert this into a complete ionic equation. Let's dissociate everybody into its ions. So this coefficient of 2 needs to be distributed to both of these. So save yourself some room, right? This is going to be 2Na plus AQ plus 2 Br minus AQ. Do you see why we did that? Because that coefficient of 2 is in front of the molecule as a whole. So you got to distribute it to both. Then we say plus Cu2 plus AQ plus, what about this 2? What does it come out as? A coefficient. Plus 2 NO3 minus AQ. Is everyone with me on how we broke up the reactants? Yes? Now, if you need to go on to a second line, that's fine. Just make sure I can read your work. Okay, this coefficient of 2 is in front of the whole salt, so it needs to be distributed to both. So 2 Na plus AQ plus 2 NO3 minus AQ. Now we break up the other product. Cu2 plus AQ plus 2 Br minus AQ. So there's no precipitate here, is there? There wasn't one product that we just left alone, right? We dissociated everybody. So when I go through and I cross out my spectator ions, what am I going to get? Everybody's a spectator ion, right? Because look, I've got 2 Na plus, 2 Na plus, 2 Br minus, 2 Br minus, Cu2 plus, Cu2 plus, 2 NO3 minus, 2 NO3 minus. Everything cancels out. So did a reaction even occur? No, right? All you did was you just mixed two solutions together and they stayed dissolved in each other. So that's why we say no apparent reaction. No apparent reaction, right? Both products are soluble. We didn't actually make a precipitate. This would make for a very boring lab. There'd be nothing to filter and dry and record the mass of, right? This would just be two things dissolving in each other and they dissolve. So if you took blue sports drinks and you dissolved it in green sports drink, right? You mix those two together. It tastes kind of weird, but there'd be no precipitate. Nothing would happen. That's the same thing here. This is no apparent reaction. Does everyone understand how NAR works? There's nothing to write a net ionic equation for. You can't. It's impossible because everything gets canceled out at step 2. Everything's a spectator. Am I okay to erase the board? Yes? All right, let's do something similar. Now instead of solutions of, let's do silver 1 nitrate and calcium chloride. All right, let's go over this one. So the first thing we need to do is write, oops, it's probably too high for the camera to pick up. Silver 1 nitrate, so that would be Ag with what charge? +1, and nitrate is NO3 minus, so that would be, this is my molecular. What's that formula going to be? AgNO3, and it's a solution, so all solutions have the subscript AQ. Okay, calcium has what charge? Calcium ion has what charge? +2, and chloride is Cl with what charge? -1, so when I crisscross those, that's going to be Ca, Cl, 2, right? It's a solution, so AQ. Okay, this is a double displacement reaction. So my products, Ag plus is going to get together with Cl minus. So what's that formula going to be? AgCl. We'll look up the solubility in just a second. And now our other product is going to be calcium ion. It's going to get together with nitrate ion. So what's that formula going to be? Ca what? 2. NO3, 2. All right, let's balance this, and then we'll look up our solubilities. We're going to need some coefficients. Where's the coefficient going to need to be? 2 in front of AgNO3 and AgCl. That's right. Because we need 2Ag, 2Ag, 2NO3, 2NO3, 1Ca, 1Ca, 2Cl, 2Cl. Okay, now let's look up the solubilities of these two products. So go back to your solubility rules. Most chlorides, bromides, and iodides are soluble except Ag, HgP, BHG. So what would we say for this AgCl? It's the solid, so what subscript does it get? S. And then for nitrate, nitrates are super easy because what is nitrates rule? All nitrates are soluble, no exceptions, so that CaNO3 is not Ag, a Q, right? Yeah, a Q. Okay, that was our molecular equation. Now let's do complete ionic. Okay, this 2 in front gets distributed to everybody. So it'd be 2 Ag plus AQ plus 2 NO3 minus AQ, right? Plus Ca2 plus AQ plus 2 Cl minus AQ. Does everybody see how we broke up the reactants? Everybody with the AQ subscript gets broken up into its ions. Coefficients in front get distributed. Subscripts become coefficients. Now let's do the products. What do I do with this 2AgCl? It's got an S, so what do I do with it? Leave it alone, don't touch it, right? So you just write it as is, 2AgCl(S). Just leave it alone. Don't mess with it in any way, just leave it be. And then we've got to break up our other product. Ca2 plus AQ plus 2 NO3 minus AQ. That's our complete ionic equation. Like I said, if you have to go on to a second line, that's fine. Just make sure I can follow your work. So the complete ionic equation is redundant because there are things in it that aren't really doing anything, right? For instance, nitrate, is it really participating in the chemistry? No, it's a spectator, right? If I go watch March Madness, I'm not actually participating in the game, am I? I'm just observing. I'm a spectator. What's the other spectator? Ca2 plus, right? So cross it out. So what you're left with is the net ionic equation. 2Ag plus AQ plus 2Cl minus AQ produces 2AgCl(S). And now since all of these coefficients are 2, 2, and 2, you can divide through and make it the smallest numbers, right? So if this were like, 9, 9, and 9, you could divide them all through and make those smallest numbers, right? So that's no big deal, 2, 2, and 2. They're all 2s, so really it's 1, 1, 1. And this is what actually happens. Everybody else is just floating around in the solution. They're not doing anything. So if you could see your molecules in ions, you would have your solid down here on the bottom. Remember, solids have a regular repeating arrangement. We call that a crystal lattice. And then your Ca2 pluses are just floating around, and your nitrates are just floating around. Right? There's your solid that you formed, and then the rest is just floating around. Does that make sense? So if I said, what are the spectators, you would say Ca2 plus and NO3 minus. Make sense? Makes sense. So on the page, starting here, I've given you 7 to try. That was nice. I gave you the formulas. So I want you to write balanced molecular, complete ionic, and net ionic equations. If there's no apparent reaction, explain why there's no apparent reaction. I'll zoom it back to that part, and so that people watching this online can have a chance to try it as well. So if you're an online student, you can just pause the recording, try it for yourself, and then hit resume when you're ready to see the answers. So write balanced molecular, complete ionic, and net ionic equations for the following combinations. I got a little bit lazy with my subscripts there. I think you can still figure it out. So I'll pause the recording and give you a chance to do these 7. All right, so we've had some time to work on these. Let's go over them and see if we're in agreement. All right, so magnesium carbonate and lithium chloride are going to make Li2CO3, which is aqueous, and MgCl2, which is aqueous. So what's this one going to be? Is there a molecular, is there a complete ionic to write? I mean, you can, but it's all going to cross out. So this one we can just identify as NAR. So on a test, if you get both of these are products that are aqueous, you could say no apparent reaction because both products are soluble. I have lithium carbonate soluble. I didn't. Yeah. No, all group ones are soluble with carbonate. Oh, well, that's dumb. It's all of group 1. So that would be lithium, sodium, potassium. I don't know why it doesn't have lithium listed on there. Sorry about that. All of group 1 is an exception on that one. I'll make sure not to give you this chart on a test. Because yes, that's definitely soluble. That would be no apparent reaction. You would not be a precipitate there. Sorry about that. So just NAR. NAR, and then you'd say because both products are soluble. Make sure you tell me that too. Okay. Write your molecular and then say no apparent reaction because both products are soluble. So yes, that's the solubility chart's fault, not mine. Woo! Making sure I didn't write something wrong. Just make sure that, I'll just make sure to tell myself not to give you that one on the test. Okay, KOH and CrNO33. Let's give some space. KOH, NO33. So we're going to get KNO3, which is aqueous, and we're going to get CrOH3, which is insoluble. All right, so we're going to need a 3 here, and we're going to need a what? 3 here. Okay, so do you want me to show the complete ionic, or can I just skip straight to the net ionic? Skip straight to the net ionic. Okay, So skipping straight to the end, that net ionic, we get Cr3 plus Aq plus 3OH minus Aq produces CrOH3 solid. Do we agree on that one?
Yeah. Does it matter if the CrOH is?
If you flip the order there, makes no difference.
Okay.
No, that's like 3 plus 1 or 1 plus 3.
Okay.
That makes no difference. Yep. How do we feel about number 2? Thumbs up. Thumbs up. All right, let's look at number 3. I could probably do number 4 on the same screen too. All right. So this is, we're going to get ammonium chloride, NH4Cl, which is aqueous, and we're going to get calcium phosphate. What's that one? Solid. That one is your precipitate. All right, so we need to do some balancing here. All right, let's see, we're going to need 6, right? Yeah. And a 3, 2, and a 2.
Oh, I have the 2 in front of the NH4.
Right. Yes. Okay. So, do you want to do the complete ionic, or can we go straight to the net ionic? Go straight to the net ionic. The net ionic equation is what forms the precipitate, right? So you're going to get 3Ca plus 2 Aq plus what? How many? 2 PO4 minus produces Ca3 PO4 2 solid. Any questions on this one? All right, number 4. Let's give some room here. Well, try not to do that, but oh well. So we're going to get barium sulfide, BAS. What's that? Are sulfides on your solubility rules? I think sulfides are on that handout. Sulfides, yes. Sulfides are insoluble except Na, K plus, NH4 plus, and the alkaline earth metal, which is group 2. Group 2 is barium in group 2. Yes, it is. Where'd my page go? So that is soluble. That is soluble. It's group 2. So that's AQ. And sodium acetate. So that's, we're going to need a 2 here. NaC2H3O2, and all acetates are soluble. So here, again, you would say no apparent reaction because both products are soluble. So on a test, if you wrote the complete molecular equation, make sure you put subscripts and then say NAR because both products are soluble, then you're free to go.
So you don't need to work it all out?
Nope, unless you just want to. All I need is this and then an explanation, all right? Write the molecular and then tell me why. Why? Because both products are soluble. All right, let's look at the next one. Okay, so we're going to get sodium hydroxide. And we're going to get aluminum sulfate, also soluble. So we need to balance this. How do we balance this? 3, 2, 6. 3, 2, 6. 6 3, 2 and 2, and 6 and 6. I agree. And then again, you would just say no apparent reaction because both products are soluble. Do we agree on this one? All right. For 6, we've done one very similar to this already. AgNO3 plus KBr. AgBr is insoluble. So AgBr, that's our solid. And KNO3 is aqueous. So our net ionic equation would be Ag plus Br minus produces AgBr, which is a solid. Do we agree? Yeah. And then lastly, we can squeeze this one on the same screen. We're going to get calcium nitrate, CaNO3, 2, which is aqueous, and we're going to get FeBr2, which is aqueous. So what's the conclusion here? No apparent reaction, and then again, have to be in the habit of saying why, because both products are soluble. How do we feel about these kinds of problems? Okay. All right. Any questions on this? So that's where we're going to stop for today.